So what we are going to talk about today is optimization. So we're going to take these ideas we learned last time about marginal benefits and marginal cost, and we're going to take the thing we did, the exercise we did at the end, thinking how big of a house I should build, and we're going to expand that. So let's try to remember what we were doing last time. Last class, when deciding how big of a house to build, which of the following was true? I kept making my house bigger as long as marginal benefit was greater than marginal cost. I chose the house size that maximized marginal benefit. I chose the largest house size available. Yes, I kept making my house bigger as large as marginal benefit was greater than marginal cost. Remember, for B, your goal is not to maximize marginal benefit. The maximum marginal benefit occurs on the first square foot of house, because that's when you're putting in, I guess, probably a toilet. The first bite of ice cream, because that's the one that tastes the best. You want to maximize your total benefit, which you get by building as long as marginal benefit is greater than marginal cost. We're going to continue on this idea today. So back here, the answer was A. So when we did this last class, marginal benefits and marginal costs each had only a few possible values. So we used this table. And this right here, if you remember, I did one and then I let you do one. This is the one that you did after I had adjusted the marginal benefits. So main thing to note here is that there were only three possible values for marginal benefit and two possible values for marginal cost. Well, usually marginal benefits gradually decrease and marginal costs gradually increase, meaning that each unit has a slightly different marginal benefit and marginal cost. Essentially, things happen more gradually. Here we had to do stair steps just so I could fit it in a table. If each square foot of house has a different marginal benefit and marginal cost, then making a table isn't practical, right? So imagine if the marginal benefits decrease gradually. So like we talked about with the ice cream, second bite's a little less enjoyment than the first, third a little than the second, and so on. Well, if that were the case, it would be very difficult for us to make a table that was useful, right? It would be this huge table, wouldn't fit on a slide, wouldn't even fit on a piece of paper. So is there some better way that we can do this? Yes, a graph. A graph can easily convey all of this information, right? Points on a graph represent marginal benefits and marginal costs at different square footages. So let me show you what I mean. So we got this table here, and I sort of stopped showing the table after 3 lines. So now we're saying that every 100 square feet, the marginal benefit goes down by $1 and the marginal cost goes up by $1. Should be the same as saying for every square foot, marginal benefit goes up a penny or down a penny. Okay. So let's go ahead and think about what graphing these would look like. So, all right, let's first get our axes in order. That's especially now that we're first starting to do graphs. We want to make sure that we're focused on this. So the bottom is our square footage. So down here we have square feet. So we have 0 up to 2,500. The y-axis is dollars. So that could be dollars of marginal benefit or dollars of marginal cost. And let's start graphing. So first we see that at 100 square feet, marginal benefit is 129. Marginal cost is 101. So we have our marginal benefit here, our marginal cost here. And we'll go now to 200 feet. Benefit goes down just a little bit to 128. Cost goes up just a little bit to 102. And we can keep this up and draw all those dots. All that's left to do is connect the dots. And now we have 2 lines. And this is something you've seen in your math classes for a long time, is graphing a line on the XY plane. Well, what we've just done is graphed marginal benefit and marginal cost. So what do I want to do? Well, we said before that I wanted to build a 1,500 square foot house, and that still holds here. Why is that? Because we said we're going to continue building as long as marginal benefit is greater than marginal cost, and stop once we get there. Because remember, this right here is the region where the benefit of 1 more square foot is greater than the cost of 1 more square foot. So benefits in green, cost in red. So bigger, bigger, keep building, keep building, keep building. Once we get here, that's no longer the case. Beyond here, if I were to keep building, my cost, which is in red, is bigger than my benefit, which is in green, which means I would be a net worse off from building my house any bigger. So now let's think about this more broadly. So more broadly than just this idea of how big am I going to make my house. Usually, we have decreasing marginal benefits and increasing marginal costs. This means that marginal benefit slopes down and marginal cost slopes up. So let's see what that looks like. This is just taking the graph we saw before and kind of stretching it out a little so it's easier to see the slopes of everything. So again, if marginal benefits are decreasing, that means that as quantity goes up, price goes down, which means marginal benefit slopes down. On the other hand, marginal costs are increasing. So when the quantity increases, marginal cost increases. So this could be the marginal cost of building a house or the marginal cost of anything else. As long as marginal cost slopes up, which it usually does because marginal costs are usually increasing, as long as that's the case, then we're going to get this upward slope of marginal cost. So now we could see some general rules. So if we have decreasing marginal benefits and increasing marginal costs, which we said is usually the case, then we get a graph that looks like this, which means that if marginal benefit is greater than marginal cost, we're in this region of the graph over here on the left side. And what that means is you should do it more. On the other hand, if marginal cost is greater than marginal benefit, you're doing it too much and you should do it less. This is the idea you built too big of a house, and so the amount you're spending on the house is greater than the enjoyment you're getting out of those last few square feet. Put them together. If you're in this region, you do more. If you're in this region, you do less, which means that when you're right in the middle and marginal benefit equals marginal cost, then you should stop. That is the amount that is best for you. And this idea works for everything from study time to work hours to home buying to ice cream eating. It's a really powerful idea that keep doing it as long as marginal benefit is greater than marginal cost. And so the best thing for you to do, your optimal decision, is to do whatever it is up until the point where marginal benefit equals marginal cost. Any questions there?
So rather than stopping like right before marginal benefit equals margin, like right in that one piece of data where marginal benefit is greater than marginal cost, you want to stop right where they cross?
Yeah, that's the easiest. I mean, like, it's one of those things you could say you want to stop right here, or like, exactly on the point. It doesn't really matter. We just say stop at the point. The very last unit, so the last square foot of house you buy, is that it'll cost you whatever it was, $125, and benefit you $125. So you're essentially no better off or worse off. So the easiest thing for us to say is you're going to do it right up until the point where they're the same. Now let's try to apply this. Suppose that for studying economics, you have decreasing marginal benefits in terms of your grade and increasing marginal costs in terms of how much you dislike studying. When you go to bed the night before your midterm, you note that for the last hour you spent studying, the marginal benefit of studying was less than the marginal cost. Which of the following was true? You studied the right amount, you should have studied more, you studied too much. So this probably, when I first learned this, brings up a question. Does anyone really think like that? Right? One critique of this methodology is that this is not how people actually make decisions. You probably have never put a per bite dollar value on a pint of ice cream. When I was house hunting, we had a general idea of how big of a house we wanted, but we did not have a per dollar square foot. If we had two houses we liked, exactly how much more I would be willing to pay for a house that was 25 square feet larger. one of the things that I want to emphasize, and this is something that you'll see throughout economics, and if you're fortunate enough to go to graduate school, this will be something you think about a lot. The goal is not to replicate the decision-making process. So I am not trying to suggest that this is actually how you're going to make the decision of how big of a house to buy. The goal is to replicate the results of the decision-making process. So what that means is we notice that when things are more expensive, we buy fewer of them, right? So when the house gets more expensive, we buy less of it. When the ice cream gets more expensive, we're going to eat less of it. And even when ice cream is free, people tend to eat a moderate amount. Why is that? Why is it that when ice cream is free, oh, I like ice cream, why do we not eat all of the ice cream there is? Because marginal benefit is decreasing, which means that eventually you get to the point where having a little bit more ice cream doesn't make you any happier at all. So you stop eating. Now here's a couple of examples I'll show you from the world of economics. So I mentioned on the first day of class that one thing that economists have looked at is, do football coaches punt too much? And so it was, I guess it's probably coming up on almost 20 years ago, maybe a little bit, 15 years ago, a famous economist wrote a paper about this. And this is the math that he used to try to solve it. And this is essentially the math that he used to calculate what is your expected extra points added by punting or kicking a field goal on fourth down versus what are your extra points added by trying to go for it on fourth down, which is essentially, if you don't know much about football, it's just sort of a higher risk strategy that can lead to more points, but also lead to some bad outcomes. And so he was not suggesting in his paper that the football coaches, evil geniuses though they may be, were actually doing this sort of math. Otherwise, what he was really thinking of was, well, football coaches do this a lot. They have to make this decision a lot. They practice a lot. They can see a lot of football games. They can see, oh, last time I tried to go for it and I didn't get it and I lost the game, something like that. So instead what they did was, with the idea here is that based on experience, are coaches actually learning to do the right thing and punt when they should and go for it when they should? And essentially what he found was that football coaches were too conservative. And this is something that has generally been supported by a lot of other analysis. So again, we want to emphasize here that the goal is to predict behavior. This is different from replicating the decision-making process. Again, no one is suggesting that football coaches do or should do these, they're called Bellman equations, every time it's fourth down. Here's another example. This is actually from my dissertation. So my graduate school dissertation was about franchising. And so I was modeling the choices made by people in Texas who were deciding which bar or restaurant to go to. And this right here was the decision that was faced every time you wanted to spend $1. And every dollar you spent at a restaurant, you did this equation. This was, again, at no point did I think that this was a realistic approximation of how people actually decide where to eat. What I was doing was trying to approximate the decisions that people make when they are trying to decide where to restaurant. And what I was really getting at is when you choose a restaurant, you consider all of your options and prefer not to drive a long way. So essentially that's what was going on here was you didn't like driving, and so you preferred places that were closer, and you thought of all the different places and spread your money throughout all the places that are close to you. That was the idea here. And again, I was not trying to say that that's how people make decisions or should. This was just a way of showing with math the decisions that I expect people to make. Here's a non-economics example. Now imagine I were to ask you, how do you parallel park a car? And if you're someone who can drive and parallel park, you could, I could get in your car and you could do it. And you would back up and you would turn the wheel and so on, and then you'd be parked. Now, what if I were to ask you to describe exactly how to do it? So you probably could not tell me. Well, you need to put about a ½ pound of pressure on the steering wheel, get yourself going to 1.5 miles an hour in reverse, and then turn the wheel 45 degrees, do that for 15 feet, straighten the wheel out, turn it forward, go forward a mile an hour, and so on. That's really not how you could do it. So again, what we're not trying to do is have you be able to describe exactly how exactly you go about doing it. What I want you to do is just show me you can parallel park. And that's what really matters. The next thing I want to talk about is how economics as a science. So economics is in the School of Social Sciences at MSU. And here's why. Here's what we think about with the scientific method. You observe something, you try to explain it, and then you test it if possible. So here I have a picture of Einstein. And so some of his theories of relativity, when he came up with them, almost 100 years ago, there was no way for him to test them. The technology didn't exist. And then in the last 10 years, actually, the technology has gotten to the point where they've been able to confirm some of these theories that Einstein came up with 100 years ago. So that's kind of cool that he had this idea. People thought he was probably right, and now we've actually shown that some of these things he has about space-time have been shown to be correct. And so this idea of the scientific method is something we're going to talk about here. This is called Why Economists Love Models. So if we think of, you've probably heard a lot about models in economics, and you've probably heard a lot about how bad they are and how they're unrealistic and they seem goofy. And you have to learn about it in school, and they have no bearing on the real world. And so what I'm going to talk about now is sort of the value of models. So a model is a way of simplifying something complicated. We lose some of the details, but keep the parts we need. So one example is that when you are first when you're first about to be a parent, sometimes you go to one of these parenting classes. I think we went to one, it was really dumb. Anyway, and so one of the things they'll have you do is learn to change a diaper. Well, it's best for you to not learn to change a diaper while you are dealing with an actual baby. Your first time changing a diaper should not be when the baby is sort of thrashing its arms and legs. Although I think that was probably my first time doing it. Anyway, so instead what they will have you do at these parenting classes is they will give you a baby doll, give you a diaper, and say, put the diaper on the baby doll. And so what's going on there? Well, we are losing some of the details. So we don't have an actual baby. We don't have all the squirming, but we keep the parts we need: torso, legs. So we learn on this thing. So on this doll is a model of a baby. We take something complicated, a small person, simplify it to get it down to the important parts, what we really need, the legs and torso. Couple of other examples. So in high school chemistry, you probably saw something that looked like this. This is an atom. We got the proton and the neutron in the middle. We got these electrons sort of orbiting around it like the Earth orbits the sun. Well, then you find out eventually, maybe if you get to college chemistry, that all of this is a lie. And that actually they look more like this, where the electrons are not orbiting, they're sort of flying around chaotically. But this right here, for what we're trying to do, what you're doing in high school is sort of learning how sodium and chloride come together and bond and make salt. So for that, this is a perfectly adequate measure. And in fact, models aren't useful unless they are solvable, right? So if I give you this model when you're in high school, there's really not much to do with it. I saw it when I was in college and I couldn't do anything with it. So what we want to think about is balancing accuracy and solvability. And really accuracy is more like usefulness. So we want to think about the goals of the model, right? So again, if our goal is just to show how one element and another element come together to make a compound, this totally adequate. This right here, if you take upper level econ classes, you will likely see what this model here, that is a painting of a helicopter dropping money out. This is actually when I was in an intermediate macro class, the very first we learned of the government was as a helicopter dropping money out of the sky. Obviously, that is in no way resembles how a government runs. But for what we were doing, we were learning about how currency gets printed and the effect of increasing currency. This was actually a very adequate model. So this whole thing was a digression to sort of explain to you why I think models are a useful thing and why we're going to talk about them here. And so instead of focusing on all the things that are missing from the model, we're going to try to make sure we're able to see if we're able to get useful insights from the model. So here we have a simple model of production. So let's start off with thinking about what I said about the scientific method. So we observe something, we try to explain it, and we test it. And so right now we are going to start off with an observation. People tend to specialize in what they do. So what that means is most people do not try to do everything that needs done in your life, right? So here's an example. Football players, big, very strong, tend to hire movers. Now, chances are that when the football player hires a mover, the mover is going to be less strong than the football player. And so maybe it'll take, 3 or 4 movers to move the chest of drawers out of your bedroom. The football player is strong enough that he could have done it himself. Another example I've seen similar to that is that Martha Stewart pays someone to clean her house. Martha Stewart has literally written books about the best way to clean. She has better things to do than clean her own house. Similarly, surgeons and car mechanics sort of stay in their lane, by which we mean most surgeons are not trying to fix their own cars. Most car mechanics, hopefully all car mechanics, are not trying to do their own surgery. Another example that I thought was good is that if you think about when you hire someone to deliver you food from DoorDash or Uber Eats, what you're essentially paying for is this person drives to a restaurant, gets food, and drives to your house. Well, you're probably better at that, navigating from the restaurant to your house, than a delivery driver is, because you know where your house is, and the delivery driver is probably using a GPS and having a hard time figuring out exactly which mailbox is yours. So that's our observation, is that people often specialize. And not only that, people will outsource tasks. People will hire someone to do a task, even though that person is worse at it than you are. So even though the DoorDash person is worse than you are at driving to your house, you're still hiring someone to drive to your house. One more is that The Rock does not do his own stunts. The Rock, obviously, very strong history of professional wrestling, so he knows how to do stunts. He has a stunt double who I think is like his cousin or brother-in-law or something, does his stunts for him. So why is this? So what we're going to do is we are going to try to explain it. So we're going to use one of our fundamental principles, opportunity cost, to explain why and how this happens. And this brings us to this simple model of production that I promised you. And we are going to suppose that LeBron James has not taken economics, and so decided against our better judgment that he should stop playing basketball and open his cupcake shop. And we're going to say that his cupcake shop has plenty of every ingredient except cocoa powder. In fact, this shop has 20 tablespoons of cocoa powder. Chocolate cupcakes require 1 tablespoon per cupcake. Double chocolate cupcakes require 2 tablespoons per cupcake. So this is the all the information we need to solve these problems. So here's a summary up here. And our first question is, if LeBron only makes chocolate cupcakes, how many cupcakes can he make? Good, 20. Again, I know this is starts off really simple, but we're doing it for a reason. I want to make sure that we start off again with a simple model. And then we'll get some really good insights out of this, but we have to start somewhere. So we can put this in a table, and we could say one option is he can make 20 chocolate cupcakes and no double chocolate cupcakes. Next, suppose he only makes double chocolate cupcakes. How many can he make? Well, 20 tablespoons of cocoa powder, 2 tablespoons for each. 20 divided by 2 is 10. So another option is he can make 10 double chocolate cupcakes. Okay. All right. So this right here is what we call a production possibility schedule. It's a table that shows the possible combinations of 2 different goods or services that can be produced with fixed resources and technology. So that's what we have here. Fixed resources is just 20 tablespoons of cocoa powder. Technology is sort of the bakery, whatever else. Come on down. There is. And the main thing we do here is for the production possibility, try going around this way, there's cords everywhere, is the production possibility schedule can illustrate trade-offs. The table can show a few possible combinations, right? We showed sort of the 2 extremes, only chocolate, only double chocolate. The graph can show all of them, right? So a graph would look like that. We take Double chocolate of 10, we take 20 regular chocolate, we connect the points, and these are all different options that he could make. And again, if you go back and look at the slides, you can see one other one that was in the middle. I think we're probably, I don't want to belabor the point here. So the main thing to note is this production possibilities frontier is a graphical representation, that thing right there, of a production possibilities schedule. Next thing we're going to do is learn a couple of terms. So the first is attainable. Attainable is a set of goods that could be produced. So in this case, attainable means some combination of chocolate and double chocolate cupcakes that LeBron could make. So for example, right here, this would be an option for him. He could produce, we'll call it like 2 chocolate cupcakes and 5 double chocolate cupcakes. And the fact that that is inside this red line means that it's possible. He could also do something like produce no chocolate cupcakes and 8 double chocolate cupcakes. Notice that in all of these, we're going to think about, especially you can pretty clearly see in this one, he's going to have some cocoa powder left over. And so that brings us to this next term, which is efficient. Efficient means is an attainable set of goods where, and this is sort of a more math-heavy definition, when you produce this set, there is no way to produce more one good without producing less of another. And again, this is sort of math-heavy. What we're really saying here in this example is that you're using all of the cocoa powder, right? So if we think about this point right here, so this right here is attainable. However, it is not efficient because if you're here, you're leaving some of your baking powder cocoa powder unused. You could instead produce more of both goods and wind up there. So here, an attainable set is one for which you have enough cocoa powder, and an efficient set is one in which you use all of the cocoa powder.